All right, and so now, wow, this is great. Such a fabulous tool to find a derivative. And of course, anyone viewing this video, you probably just as beginning as anyone else. And so you will keep exploring how useful this new technique is. But now let me erase the board and immediately bring you into our first example. And for the first example, I would say we're going to stay right here with this equation, but let's develop some good example out of this thing that we've done. So all the work we have done here is not even a formal example. It's just to show you what it means by taking the derivative implicitly. Or yes, ladies and gentlemen, you have found the first problem. You have seen the first problem where we apply implicit differentiation. The process that we did, that we find the derivative without solving for the variable as an explicit function of the other variables. Then we call that the implicit differentiation. So now I am going to erase my board. All right, so let's now get into example 1. All right, and so for my example 1, I'm going to start out by saying we are given an equation. So how about x squared plus y squared equals 4. And for any viewer watching this video, I have a little friendly warning. Go ahead and, as we go along with this video, but before I start, go ahead and have for yourself or recall for yourself what the graph of this equation looks like, okay? And before I get there. But now, back to the problem itself. We are given this equation, x squared plus y squared equals 4. And now part A of the example. We are going to find the slope of the tangent line. Okay, find the slope of the tangent line. And the tangent line to the graph, of course, that's why I was asking for viewers to go ahead and have a picture or recall for yourself the picture of this equation. You got tons of web resources in these days to quickly graph the. Thus, you have the most basic reach, your TI calculators, or over the web you have Desmos or GeoGebra, all of those free resources that quickly graph these equations for you. So, but what I want in this problem here, find the slope of the tangent line to the equation, okay? Or I don't even have to say to the equation anymore. Of course, it's the tangent line to the equation. I can just say find the slope of the tangent line. But here at the given point, how about square root of 2, comma 2? All right. So before we get any further into the problem, so here's the thing. If anyone noticed and follow really closely along the video so far, this is the first time throughout many of my lectures that you have seen. This is really the first time where I'm asking in the problem to find the slope of the tangent line just as usual. We need a derivative. But this time, instead of giving, you see in any of the earlier problem, it's all about find the slope of the tangent line to the function, to the equation, whatever, but at, and then x equals, and we only have an x value given. But here now we are given as a full complete point. So before we get started, anyone must understand this is our complete tangent points. So we already had the tangent point given, okay, and I call it, it's the complete tangent point. X coordinates, Y coordinates is here. X value, Y value is here. And I want to find the slope of the tangent line. The slope of the tangent line at that point right here. All right, and so let me get straight into the math, and then I will be showing the graph. And hopefully you already had in mind some picture of the graph already. But so, and that's why I'm bringing up this example after I worked out the derivative. So we can just take that work. We don't need to reinvent the entire wheel. Implicit differentiation let us, and you have seen that all in my earlier part of this lecture. So dy dx in this case already known to be negative or minus x over y. Okay, minus x over y. And that's simple, because I can just take the answer from our work we have done previously, even though earlier work was not even an example. But it was a work, it was a math work. And we can just take things from what we have had. But now, I emphasized earlier that our final derivative, our final general derivative earlier was involving two variables. And this is where it's becoming useful over here, because with a complete tangent point given like this, with a tangent point given in a complete pair of x and y value, then we know what to plug in. X substituting in for x, y substituting in for y, and that particular final value after evaluation is going to be our slope of the tangent line. And so now, once we recall for ourselves the derivative out of this equation in terms of x, then the slope of tangent line. And now allow me to erase these extra writings so that I can maximize my board space right here. But so that means the slope of the tangent line, and I will permanently using slope is lowercase m, but with a subscript capital T right here to indicating this slope with this value we're about to find. It is the slope of a line. But the special line here is the tangent line to this equation at that given point. So the slope of the tangent line here is, and as a general indication of what to do, the dy dx we have found previously. Substituting in, and I also introduced this a little while ago, substituted in this pair of values square root 2 comma square root 2. Okay, so that means we are going to have minus as the overall minus for the expression, square root 2 substituting in for x, and square root 2 the other square root 2 substituting in for y. Our slope here, our final slope of the tangent line is concluded to be -1. So we found the slope of the tangent line. All right, so I am not going to rush into part B. Yes, we are done with this, but let's give some good interpretation of that. Okay, so let me prepare my Microsoft Excel screen, my decimal graphing calculator, and then I'm gonna quickly put it on screen right here for anyone to view it. Okay. All right, so here we are now, ready for that. Okay, so now let me immediately put on screen. So here's my favorite graphing calculator. All right, the decimals, so you can visit that right at decimals.com right there. But the equation x squared plus y squared equals 4 is going to give us a graph like this. So quickly recall for yourself, it's a circle. The circle with the center right at the origin 0, 0. And that's what x squared plus y squared equals 4 is. Okay, so that's the equation, that's the graph for this equation. And by the way, the 4 here is 2 square, and that's why in our function, the radius of this circle is 2. So, but that's just the algebraic understanding of our of the graph. So now the tangent point is here. Okay, and so now I'm going to go ahead and put the tangent line. So the tangent line now in green is this green line right here. So this line is tangent to the circle at this point given at, so decimal sadly only gives decimal, but 1.414 is about square root of 2 right here for the x coordinates, and 1.414 again is about square root of 2 for the y coordinates. So in other words, at my tangent point right there, we have this slanted line in green being our tangent line. But so we calculated the slope of the tangent line here to be negative 1. Well, for now, immediately looking at the graph without knowing much about the precision, then it does look like the graph here, the line in green, the tangent line is having a negative slope because it's pointing down from the left to the right. And so now if I put grids, if I put on some actual grids right here, okay, and that's the powerful thing with decimal. So you can see that, you see whichever points here that the graph started at the y-intercept here, and then it hits down here, it seems like it's dropping down as a equal ratio. It downs that much by that much. So it makes sense that the slope of this line is being the negative 1 slope right there. Okay, and so that quickly demonstrates the idea of the slope of the tangent line of this equation with the graph as given here in red at that given point. Okay, but now back into my problem. So let me even give a little further interpretation. So now this time I want to give another explanation of why we need to have the extra variable here, the other variable, or let me sort of like I'm about to give another explanation of why this our final derivative here, when after we take the route of doing implicit differentiation, usually involves two variables. Because here, look one more time at the way how our equation looks. Okay, so our equation is in the form of, I mean, once we graphed our equation, it's a circle. So think about it. If the problem at the end here, if the problem was only given, okay, so now I'm going to say what if. I'm going to have to momentarily erase that. And let me put back the kind of problem as a scenario. Let me put back the problem like how we have done that before. Meaning, we would end the instruction of the problem right at, given x equals square root 2, without giving the y value. That's what I'm saying. Okay. So this is like how we have done it prior to this point. Find the slope of the tangent line, right, to that equation but we only given the x coordinates. If that was the case in a problem like this, then unfortunately we are unable to find the actual slope, because here's the thing. Look at our graph right here. It's just the way our equation is. Once we put up the graph, then one x coordinates, we can actually turn out having two separate y. Okay, we can have a value right here, and there's another exact point being the reflection of that first point right here through the x-axis. So I'm going to surely have another point about down here somewhere. Okay, and so with the same x coordinates, and I'm having a hard time of pulling it out right there, but it's somewhere about there. So my point now is that one x value, usually when we're doing these kind of implicit equations right there, then one x value can turn into so many different y's. And that's the reason why in the problem itself right here, now we need to indicate the actual variable y, so that when we now giving the tangent point, we must give the tangent point as a complete point with x and y, so that it specifies on the same graph right here, but we might run into two separate y, same x value, but we might run into two separate y's. So the y variable here is sort of like a placeholder for us to give further information about which tangent line we're looking at, even though at the same x value we might run into two or even more tangent lines. And so here I'm looking at that tangent line specifically at the positive y, okay? Because right here is positive x, of course, but it could be positive y or negative y. So now in the problem is indicating that we want the tangent line at the positive y values. Okay, and so that was part A of the example. And in case I missed any information that you were looking for, feel free to contact me to find me through as a comment in my video, or if you're a student in my class, there are tons of ways I can provide for you to find me. Okay, but now let's step into part B of the same example here. Now that we have found the slope of this tangent line, but it's only the slope so far. So now let's complete the equation. Okay, and so part B, find the complete equation. The complete equation. Okay. Of the tangent line. Okay, at that same point, square root 2, comma square root 2. Okay, and so now from that earlier step we already had. So finding slope was already a big stage, right? So the next step now is, and we already had. So I just want to emphasize again that in these problems, finding the equation of a tangent line, the same kind of task we have been doing all over. But now if we were going with implicit differentiation, then the problem must give us the point in complete form like this. Then usually the step that finding the tangent point is sort of like being given to us. Okay, so here's a tangent point. We already had the tangent point. Again, I remind anyone that, so that's the tangent point. And so now the equation at this point for any line, y equals mx plus b, so we're looking at minus x plus b. Okay, minus x plus b, because the equation of the tangent line is negative 1. I mean, the slope of this tangent line is negative 1. And so now all I do here, and what I'm showing here on the board is only one among the many different ways. Now the viewers don't have to go with my way here, because this is more like an algebra problem now. Find the complete equation of this tangent line. So I would just go ahead and use the x value for that and substitute the y value for that, and I solve for my b value. And so now I'm looking at square root 2, substituting in for y equals negative, and then square root 2, substituting in for x plus b. And so now our final b value, after solving for this, b equals, it must be that we're looking at b equals 2 square root of 2. Okay? And if anyone feeling the pressure or feeling a little nervous about working with roots, well, after this video, I highly recommend, if you feel nervous about working with square roots, I recommend that hop on to Google and search for tons of problem deals with roots, so that you really have to get comfortable. If the class here is a face-to-face class, I keep telling my students, you have to start loving fraction and start loving root here, so that you can feel a little easier with these problems in calculus. Okay. So that's our b value, our y-intercept of the tangent line. So our final equation of the tangent line now is y equals minus x plus 2 square root 2. Okay, so that's the y-intercept. So slope negative 1 and y-intercept at 2 square root 2. And that's the reason why, one more time, let's look at the graph right here, and we saw that in this graph we currently have this value right here where the green line crosses crosses the y-axis, that's value right there in decimal. Sadly, that's all the decimal can do, but it's about the decimal expansion for 2 square root 2 right there. Okay, so that completes our example 1 in this problem. Okay, and so now I'm going to need to take some time again to erase the board. And before I bring everyone into the next problem. Okay, so now let me discuss why is implicit differentiation, I've been calling that a fabulous solution. So why do we need it? I mean, why is it so good? Why is it so good? I wouldn't say it's the better technique because it all depends on the situation. So in our particular problem in this case, recall for yourself that we started out, even before we got into example 1, our equation was x squared plus y squared equals 4. Okay, and if we went with the explicit route, so now I have to recall for anyone. Okay, if we really want to spend time and solving for x, solving for y, x squared plus y squared equals 4, then it takes about 3 or 4 algebra steps, provided that you are brilliant at algebra. Then you can quickly do y squared equals 4 minus x squared, okay, because we're solving for y explicitly, and I'm kind of going back to that, rolling back to that kind of work where I had to stop in the middle right there. So y squared equals 4 minus x squared. Then y equals, so now notice it's not just simply one function, it's 2 functions, plus y equals the positive square root of 4 minus x squared, but now it's explicitly defined as a function of x. But then there's also another function, y equals negative, same y can also equals negative of this square root expression. And so from there, one more time, let's look at the equation. Okay. So now here's the equation. You see, the positive square root of 4 minus x squared is this upper dome if we're thinking about breaking this circle into 2 separate functions. I'm going to put a point here, and I'm going to put a point there. There are 2 points here. So anywhere above the x-axis, that's the curve positive square root of 4 minus x squared right there. And then the bottom part right here, or kind of like a bow right here, okay, the semi-bow, the semi-circle at underneath the x-axis here is the other function's negative square root of 4 minus x squared is down here. And so one equation, but now if we're solving for y as explicitly as a function of x, then we're running into 2 separate functions. And then from there, I'm going to get back to my writing board. And from there, if the problem is just simply find the tangents, then, okay, how about let me use this space right here. Recall that back in that example 1 that I was doing, then we were given the tangent point at square root 2 over 2. Okay, so the same x value, but see, y value can be 2 different y values. That's why this y coordinates must be specified. So now having a positive y value given here, that means we go back to this instruction and see how much things it's already taken out for us, and only the algebra so far. We haven't done too much with anything with the calculus yet, and so much algebra, arguments, and reasonings already. And so now we have to depend on that positive square root 2 right here as the y value to decide, because recall that here there are actually 2 functions. 2 functions here. This line right here is not one function. This line is 2 functions. Okay? 2 functions for yourself. And so we use this given information about the tangent point to decide that we must use this positive square root expression. And so now there we're going to start taking the derivative. We're going to take the derivative. So the derivative now is going to be, we're going to have to, well, even before the derivative, we have to think of the square root of 4 minus x squared here as 4 minus x squared in parentheses to the 1/2 power, okay? And so now derivative will come out being, chain rule says there's the outer function is a 1/2, so we multiply the 1/2 down, okay? And then the power reduced by 1, so 1/2 minus 1 is a negative 1/2. The inside remains the same, and now chain rule says we have to multiply with the derivative of the inside, which is in this case a negative 2x, okay? That was so much work. That was so much work. And then with something like this, the minus 2 cancel with 2, and then we're looking at minus x divided by square root of 4 minus x squared right here. Okay? And so, see, so much thing we did, and the work became so much longer. Now, in my work earlier, because the reason it took so long, because I had to explain, but talk about the process right here. If we just silently do it, and if we know both steps as a fluent level right here, then this steps here is going to be a lot slower, because we had to spend so much time bringing that into the correct equation. And here's another connection right here. If anyone going in that route, finding the explicit, taking the explicit differentiation of that, then see the square root of 4 minus x squared right here. Wait a minute, square root of 4 minus x squared, isn't that what we have decided? That's y value. That's the y value. That's the y. So that's why back in our, it's related that back to our problem earlier, we came to dy dx being just simply minus x over y. One good thing, that's one formula. And it represents for any possible expression of the y variable. Okay, so y going the long way, we go the short way. Okay, this short way is a lot more direct, and it's completely official. It's completely legal in mathematics. Okay, and so that's another way of pointing out why going this way is better. All right, and then, so, but if anyone's still not so convinced, and still love to stay with solving for, you know, out of an equation like this, where x and y standing with equal role, kind of like in line together, and still love to solve, then let me bring up a challenge like this. So this x squared plus y squared equals 4 is still not so bad for if you would take your challenge to go for solving it. Then if we go with something like this, how about x squared times y plus, okay, xy cubed, all right, and equals 4. When it gets to something like this, then I really have to say, good luck for anyone trying to solve for something like this, solve for y in terms of x, okay? And it's, the reason I'm saying this, because it's going to take a lot of work, and nothing can guarantee that we're going to arrive at the correct thing. And by the way, besides, if you're solving for y here, it's the reason it becomes a challenge, because solving a cubic has always been a big challenge for many mathematicians out there. Okay, so for us being the beginning level, it's not an easy thing at all. You see what I'm saying now? Okay, and so for something like this, then we have to definitely give up the idea about solving for y as a function of x. Or even if, you know, we're trying to solve for x as a function of y, it's not that simple either. Okay, and so that's why, you know, at this point right here, you know, knowing the implicit differentiation is a good plus right here. No, I wouldn't say it's the better methods, but at least in situations like this, it works better. So I have to clarify a couple things right here. So if your function is already, so I have to emphasize the term, if the function is already explicit, okay, or explicitly defined, okay, if it's that case right here, then good, y equals some function of x. Okay, then go ahead and stay with the usual method you have learned before, implicit differentiation. No worries, don't use implicit differentiation. It's making it a little too much. Okay, too fancy. So if it's like this, then, you know, just use the ordinary methods, okay? Meaning just any method you've learned prior to implicit differentiation. And trust me, prior to differentiation, up to the point you've learned the chain rule, you have learned enough techniques, really good amount of techniques right there already, and that can handle over 90% of functions out there in terms of finding the derivative. Okay, then just use the ordinary methods when your function the function given to you is already explicitly defined. But then in case your function is like the one I had in a couple of examples here, or it's still on the other board, like when the function is implicitly defined and written as a function form like this, that's where, okay, now I have to note here, so if, right, function is implicitly defined, okay, through an equation, and at this point, save me from too much writing right here, you know what I mean. So if function is implicitly defined, okay, then in this way, implicit differentiation is the methods that's perfect for this, okay, is good for this, for that case. Okay. All right, and so now we are all ready for stepping into example 2 now. So now it's just a matter, and I highly recommend that anyone viewing my video to independently try with me and learn from hopefully only one example we've done so far, but hopefully had an idea and be able to do independently. Okay, so the next example here, now I call that example 2. So we just simply want to find dy dx. Okay, and so in this problem right here, let's say part A, the equation given to us is x to the x cubed plus xy cubed equals 10. All right, so there we go. We have a. So now at this point, you see, back to the instruction, it's extremely critical that you watching out for being, or anyone doing the work here, you will be aware of what this symbol is telling you, because there's a whole intention behind the scene for that. This symbol intends that y from your equation is the function, and the x variable in your equation is being regarded as the independent variable that drives the value of y. So in that way, so again, remind yourself, y is the function of x. Y is the function of x. Okay? So now, learning from what we've done earlier. So right from here, it's an equality between two expressions. So I am going to differentiate, meaning take the derivative. X cubed as a one term plus xy cubed. I'm going to differentiate the left-hand side in respect to x variable. Okay, so in respect to the x variable, and if the left-hand side equal to the right-hand side here, then the result, it makes sense that the results coming out from taking this derivative should equal to whichever being the result by taking the derivative on that constant 10 on the other side. Okay, and so that's how we're setting it up as the first step. So just like how the earlier problem was, boom, I start right into taking the derivative of the x squared plus y squared, and then on the other hand, take the derivative of the opposite the term right there, opposite side. So now the easier work is here. The derivative of, see, in respect to x, in respect to the x variable, but our term here is a constant term, so completely independent with the x variable. That derivative now would become 0. Okay, and now another easy thing we can carry out here. the sum rule can be applied here, because even though we have a pretty ugly looking expression so far, but it's a sum of two separate terms here. Okay, and so in that way, feel free, and yes, it should be correct that we apply the sum rule. Okay, so now the sum rule says it's going to be the derivative, finding the derivative separately on that first term being the x cubed, and add together with whichever comes out after finding the derivative on this x times y cubed. Okay, all right, so now I am going to move on to the next term. So in my next term right here, in my next step, the right hand side remains 0. The left hand side carrying out from the very recent step. Okay, then I'm going to leave that remains the same here for now, but that step we can take the derivative now. So taking the derivative in respect to x of some term that only involves x, it's easy. This is what I meant again, explicit. So when things has already been explicitly defined, then just do the usual thing. Just do the usual thing, like the little notes I had earlier. So now, first term becomes 3x squared. That's it. Because the x cubed term was already explicitly, as a term explicitly defined in terms of x, and our derivative here is in terms of x. Okay? But now, and so I'm going to remain adding with whichever would need to come out as the derivative for x in product with y cubed right here. Okay? And so, again, more rules that you have learned previously can be applied here. More rules that you have learned, and what I mean now, so I intend here to recall about the product rule here. We have a product. We have a product here. All right, so the right hand side is done. The left hand side here, first term is done. Now we're going to keep tearing down how to find the derivative of this. All right, so now I'm going to rewrite my equation equals 0 on the right hand side. The left hand side here, the first term is done, 3x squared. Okay, plus, all right, just as the sum rule indicated. But now I mentioned about the product rule. We have a product here. So the product rule says to take the derivative of a product, we are going to find the derivative of the first factor in the product, multiply with the other factor without derivative. That's why I'm having the y cubed here, no derivative. Okay, and now I'm going to need to add. And now I'm going to leave, so maybe I need to write my equal sign a little further out to the right hand side. But now the product rule says I need to keep my first factor in the product here the same and multiply with the derivative, whichever comes out as the derivative of the y cubed right here. All right. And that's how I'm working it out. So everything I'm keeping in my square brackets right here is the product of my product rule. Okay, it's whatever the next step after we took the product rule. That's why I call it. It's the product of the product rule. All right, and once again, let's start bringing down those easy things. So in the next step, the 3x squared term stays the same because it's already done. Okay. Now in my brackets here, this is what I can have, and now we can start taking away the brackets. So derivative of x, this term is a particularly that expression here is in terms of x, and we want to take the derivative. Notice the derivative here is only for that factor x, not having anything to do with the y cubed. So that means here it's just 1. Derivative in terms of x of the function x is 1. Power 1 multiplied down and the power reduced by 1. And so here it's just 1 times y cubed. And that's how 1 times y cubed. Okay, and I don't even have to write down that 1, but just for now I just want to tear everything down into as detail as possible. Little pieces as possible. So that takes care of the first term. We already found the derivative of x here. Now I'm going to add, okay, x times And now I'm ready for finding that derivative. Okay? Or maybe let's not rush. Once again, I'm going to put that there, leaving it the same, because I want to really move on step by step. And please, one day when you're fluent enough, you don't have to follow as many steps, but the core step is the one I'm about to show right here. So, just show your steps where if you're with me or with any instructor where any calculus instructor require their students to show the steps. And so you just show those steps, highlight enough to show how you take the product rule, because products being involved, power rule, but as much details as I have here, and the little details you can skip and be a little more loose on that. Okay? But now we are ready for the next step. So in my next step, 3x squared now is done, plus y cubed, plus the x factor is here. Okay? Now, just like what we've had, y is a function of x, y is a function of x, and y is a function of x. Okay, and I hope I didn't mention that too many times to the point you're getting bored of that, but there is a whole reason of saying that, because now if y is a function of x, then look at this y cubed by itself again. Then that function of x right here means we have an entire expression of x inside of y. We have an entire expression of x inside of y. That means here we can think of that as we have some outside function, okay, being cubed. And now the entire expression inside of y, which conveniently represented by y, we put that inside here. Okay? And so chain rule now is going to apply it again. So it's extremely crucial that you got to master your understanding and how to operate with the chain rule in order to find the derivative anytime it involves the inside and the outside in your function. Okay? So now with that, then taking the derivative in terms of x, of course. Okay, now it's going to give me, the chain rule says it's derivative of the outside giving me 3 times y squared. And now, but chain rule says I have to multiply with the derivative of the inside. But since we don't know what the inside function is, we're keeping y as an implicit function of x, and as a function implicitly defined as a function of x. And that's why, without knowing what that is, we leave its derivative as the unknown, the implicit dy dx. Okay, I might have not used that term, the implicit dy dx, but now here it is, because once the function is implicit, its derivative has to also be implicit. And so here it must be 3y squared times dy dx. The chain rule is the essential, the core idea behind the scenes here in this problem. And so now I'm ready for filling in what that is. So after all that development of mine, thus taking derivative of y cubed right here truly is 3y squared times dy dx. Okay, and now equals 0 on the right hand side. All right, so now at this point we are officially done with the taking derivative action. Okay, the operation that we're taking derivative is now done, but we still need to solve for the dy dx as a final expression explicitly. So now I am going to see all these terms here are independent with the dy dx. There is no dy dx associated as a product with these things. Only that term. And by the way, that term is you can write it as a 3xy squared times dy dx. Okay. But now in the next step, I am going to subtract all these non-dy dx terms to the other side. And so in my next step, what I'm having here is 3xy squared, I'm just rewriting that, times dy dx, and to equal negative 3x squared minus y cubed. So negative 3x squared minus y cubed to the other side. Okay, and we're getting there, and we're getting there. All right, so now in my little space that remains on the board here, allow me to write it because I don't want to get back and interfere with the earlier board. So now dividing both sides, now we can divide both sides by the 3xy squared right here. Okay, so I should have just underlined that, but since I have so much narrow space there, so I'm going to divide both sides by that factor 3xy squared. So this is also divided by 3xy squared. So my final dy dx here minus 3x squared minus y cubed, but now divided by 3xy squared. All right, and so there's our final derivative. And so back in my other board right here, ladies and gentlemen, we've made a long journey, but starting out with this equation given from the beginning, and we apply, and of course because I'm teaching here in this video, so I went through as many careful steps as possible. So I hope any viewer is getting a good grasp on that. But when you're actually doing that in practice, then you don't have to carry as much steps. Only highlight those steps where it has the power rules here and the product rule is being involved here. Okay, and it shows and where that step is in showing the implicit differentiation. Those are all the steps that's being the important steps are here. And then make sure you solve for your dy dx properly. But now, so we've made a long way. So our final, on this board here, I just want to put the final answer together with the beginning problem. So dy dx here is negative 3x squared minus y cubed over 3xy squared. And at this point, forgive me if I made any typo, but anyone viewing this video should be mature enough in math to recognize any error due to typo. All right, so that's how we have done part A. So I am now going to get started on part B, and now we can start speeding up the process a little bit. All right, so part B of the example. So what about, we're looking at x squared y equals 4 minus x y cubed. Okay, and so with something like this, so now it's just an advice, okay? So here again, we definitely don't want to solve, and we want to find dy dx. So explicitly again, y is intended to be the function and x is the independent variable. But we definitely don't want to solve for y as a function explicitly in terms of x, because it's too much, way too much to get it done. Okay, but here's a little advice. You see here, what has become worse compared to the earlier examples, including the introductory problem I brought up. In those earlier problems, all the variable terms were on one side, but here the variables are all over. We got variables here on the left-hand side, we got variables here on the right-hand side. Okay? So my advice here, it's always a good practice that it's your choice, pick the left or the right, but bring all of your variable terms to one side, and kind of like we isolate out all the variable terms on one side. If you like the left-hand side to put all your variable terms, so do it. Then bring all these guys to the other side, which is I do too. I favor putting all the variable terms on the left-hand side. It's just me being like that. But you can also bring, and I should have mentioned, if once you brought all the variable terms to one side, what's left behind on the other side? All the constant terms go to the opposite side. Okay, that's my advice right there. So bring all the variable terms to one side, and then yes, bring all the constant terms to the opposite side, and then left side or right side for the variable terms to start out with. That's your choice right there. I personally will always choose to put all the variable terms on the left-hand side, but you can do the other way around. Okay, and so with that advice, I have for everyone, and I would do the same thing. So I'm going to bring that term to the opposite side. Now that term x squared y has already been on the left-hand side. So why moving it, right? Why moving it when it was already on the side that we wanted it to be? And so now I'm going to move the other term, and move, I mean, it's the algebra move, okay? So we're going to move it with the algebra work right here. That means I'm going to add both sides. I'm going to add xy cubed to both sides. And please, this is just a brief algebraic reminder. All right, and so by doing that, this term is going to go to the other side and becomes a plus. And that's what I meant by we move. So we bring all the variable terms now to the left-hand side, to one side. I chose the left-hand side. And then what remains on my opposite side is a constant term. Okay? And so now with this thing right here, that we are ready to find the derivative, the dy dx thing. Okay? So now, if this is an equation, then yes, at least you have seen this idea for a few times already. Then we can take the derivative equally on both sides. Okay. All right. That means if we can have an equation, then we can find the two derivatives equally like that, directly on both sides. And now right-hand side gives me a 0, as you have seen so many times. That's why it's always good to bring all constant to one side, because boom, it will give you a 0, getting work a lot easier for yourself. Okay, right here, then we can bring it down to, see, sum rule. So have a step to show sum rule is being indicated. Okay, and even one day when you are so fluent, you can even skip the step right here because everything is already in there. It's so trivial to see that the sum rule must apply here. So I have another step like that. Okay, and now each one of my terms right here is a derivative for a product right there. All right, so there's a product here between the x squared y, and there's another product here between the x y cube right there. Right, now in my next step, and hopefully viewers coming to this point of my video has already gained a little more majority. So I am going to start speeding up the steps a little bit. Okay, so in my next board right here, first term from the earlier step become the product rule says we're going to go derivative of x squared times y plus x squared, leaving it the same, times the derivative of y dx. So that's the product rule for the first term. And we're going to add, so I'm doing two steps in one. That's what I meant by speeding up the process a little bit. So with this product rule is going to say, it's telling me to take derivative of my x function, multiply with y cubed factor, plus, and now I'm going to leave x the same and take the derivative of y cubed, okay, and equals 0. All right, so keep track of my work right there, and feel free to pause the video anytime you need to make sure that you agree with every little one of my steps right there. And so now, hopefully you pause the video all over and agree with every single step of mine right here. Then I'm going to move on right here. So this, now you have seen that so many times up to this point, hopefully. So the derivative of x squared, it's already explicit. So now it's, so be it, just 2x. Okay, nothing fancy. Multiply with y, so 2xy. Okay, that's come out from the first term. Plus, now x squared, no derivative, but y, take the derivative of y, and we know y is a function of x. Y is a function of x. But we don't know what that is. In other words, y is implicitly a function of x. So now it's just telling us that we just have that derivative dy dx. That's it. Okay, just that derivative dy dx is here. Nothing we can do about it. So x times dy dx. X times dy dx. Okay, and now we're done with that, all that term there. Plus, now the next one, the function here is implicit. I mean, that little factor, that little expression there is explicit. I meant, okay, so x to the first power, okay, and taking the derivative explicitly in terms of x, so it becomes just 1, and 1 times y cubed, so that all that term is a y cubed. 1 times y cubed, how's that? Okay, and then plus, and now we have that step now about to be taken care of. X there times, Now this derivative, so once again, after so many times I made my logical reasoning on that, my mathematical reasoning on that, there's y is a function of x, y is a function of x, okay? So y is a function of x, that means here y, there's a whole function of x inside of y, and this y is being cubed, meaning think of that the same as some function. There's some outer function being the cube function, and inside of that there's a whole expression that we represent it by y. So taking this derivative in terms of x right here is the same as, yes, take that derivative, okay? And now chain rule says it's going to be 3y squared, a little scratch work there for the outer function or outside function, and multiply with the derivative of the inside, dy dx. And so now we are so ready, okay? And so now we have found what's that derivative of dy dx of that y cube is. Now it's going to be x times 3y squared times dy dx equals 0. All right, so at this point, officially speaking, finding derivative is done. Taking the derivative step is done. But now we have to solve for the dy dx explicitly. And so now, let's look for like terms. So this term here, and maybe let me underline that in red ink right there. So this term here is like term with that term right there, okay? And then these two are, without the dy dx associated with that. So we can go ahead and push all these two terms to the other side, just like how we've done in the earlier examples. So now I am going to have x dy dx, okay, plus 3xy squared dy dx to equals minus 2xy, and then subtract that y cubed term to the other side, minus y cubed. Okay, and I keep getting there, and I keep getting there. So now the two terms remain on my left-hand side right here. They are, at least these two terms contain the common factor dy dx. What do we do algebraically with common factor? We factor it out. So now I'm looking at x plus 3xy squared times dy dx, because this dy dx was the common factor of the two terms here. So after pulling out the dy dx, we're looking at something like this. And that all that here equals minus 2xy minus y cubed. Okay. Y cubed. All right. And so for my next step, I need to divide. See, now what we have here on the left-hand side is the dy dx as a variable and multiply with an expression here. So all we do now is just divide both sides by that expression. X plus 3x y squared, we're done. Okay, and so allow me to get back on my other board, and I'm going to have to erase and make some space right there. And of course, at this point, hopefully you have taken enough notes right here. All right, so now my final dy dx here we are, minus 2xy minus y cubed divided by what I have now is x plus 3xy squared, and that is our final derivative of the beginning equation here. Okay, and we have found this derivative by applying implicit differentiation. Okay. All right, so let me now erase my example here, all my work here, and so you have to understand at this point, even though in any of my work right here I might show the long steps and you might have found the shorter steps, that's completely okay. The answer is going to be the arriving at the same answer. It's just, I have been in the position of the person teaching here in this video, that I have to choose the one that laying down the solution that lay down as many steps as possible, so that as many viewers can follow and understand. and including all of my students right there. But so now back to before I completely erase this example. See, the whole idea I've been saying since the beginning of our lesson here is that this dy dx has a very critical understanding, and so it's fabulous if you can understand that clearly. But it intends that this dy dx symbol intends that the y here in your variable is the function, and the x in your variable in your dy dx notation here is the main variable of the equation. Okay, and so in that way, yes, if you were wondering, so what about dx dy? Because now any of these equations, like say the x squared plus y squared equals 4 you have done earlier, this is just simply an equation. I mean, without any specific indication, then which one here can be the function? Any one of them can be the function in terms of the other variable. So if we've been treating y as a function and x as the variable the whole time and only stick with that, this other variable is going to complain. I mean, why you are so unfair? I mean, this guy can be the function, why not me? So to be fair, this guy can also be a function and treating the other guy being the variable. So now you can kind of see where I'm going. So now in my example 3, okay, and here once you've had enough experience, I don't have to bring up as many problems anymore in this example 3. But here, yes, what you're waiting for is here. Let's find the x dy. Okay, so let's find the x dy. So I'm not lying, and then I did not have a typo. Okay, it's not a mistake. I am asking for the x dy. So let's look at the equation. Okay, now it's just a random choice. My plan here is I'm going to pick any of the problems we have done, and then reinvent over, but this time we're looking for the dx dy. Okay, so how about from the easiest one? The x squared plus y squared equals 4. Okay, the x squared plus y squared equals 4. The whole lecture so far, I've been doing dy dx, and y is a function of x, y is a function of x, all that, okay? But this time we're looking for x as a function of y. So I'm so sorry if I keep making you falling so far into that path saying y is a function of x, y is a function of x. But here we have to turn it upside down. I mean, turn it backward. X is a function of y, x is a function of y. X is a function, y is a variable, x is a function of y. Okay, it sounds like a joke, but trust me, if you're getting for yourself into this habit, you will get the problem done successfully. Okay, so x is a function of y. So now it's an equation, so we can x squared plus y squared. Once again, we can equally take the derivative, but this time be cautious. We twist around the convention, the instruction. We're looking for we're taking the derivative in terms of y. So it's a dy here. Okay? So that means this variable down here, this now, once we're seeing that as a variable, then that means that term now is explicit, and this term here is implicit, but we'll get there. And then right hand side, constant 4, but we're taking the derivative in terms of y. All right. And so now in that way, just all the usual rules applied again. The sum rule, the product rule, the chain rule, they're all going to apply. So right hand side is a 0. The sum rule is going to break that into 2 separate terms. D, we take the derivative in terms of y of the x squared term plus, and then the derivative in terms of y for the y squared term. Like that. All right. And so now I'm ready for the next step. So see, that square term, this term right here, see, I always tend to move on from the easier one to the harder one. So I always, and it's just my style maybe, but I always look for the easier one first. Get it all taken care of so that we can get them out of our way, and then we start taking care of the big guy being the most challenging one. Okay? So we go from the easiest guy into, rising up the level like that. So equals 0. That term now, the y squared, this time, x is in terms of y. Okay, x is a function in terms of y. even I get mixed up sometimes. Forgive me on that, but x is a function in terms of y. That means this is already an expression explicitly in terms of y. So why wander around? This thing here is just simply 2y. We don't need the d thingy here, just 2y, because it's already the explicit derivative here. Okay? Now plus that term's there. Now you got to remind yourself, x is a function of y. X is a function of y. That means this is the outside function. Let me make a little scratchy note right here. X is a function of y. That means x squared is the same as think of some outside function being square. And inside of that square, we have a variable x, which can represent an entire function of y in there that we don't know. We don't know what it is. It's implicitly defined. X here is implicitly defined as a function of y. Okay? So in that way, I shouldn't erase that. A little too rushed. But x squared equals, okay, all that big expression. So taking the derivative, okay, in terms of y now. Okay? Take the derivative. See, that's why I usually don't use this notation too oftenly, because it's easy to mix up which variable that is, but only when we already had a clear indication of some steps before. But now taking the derivative here, we are going to, the chain rule says, take the derivative of the outer function. So that gives us 2x. But now chain rule further says we need to multiply with the derivative of the inside function. So now I'm looking at the dx dy. Okay? So all that here now is a perfect substitution for this term. So now I'm looking at 2x times dx dy. Okay? And so now we are ready for solving for the final dx dy. Okay? And I don't think I need to move on to the other board right here, because all that space here is just perfectly enough for our work. This is the non-dx dy term, and this is the only dx dy term. So I'm going to bring that dx dy, the non-dx dy term here to the opposite side. So that means in my next step, I'm producing 2x times dx dy, okay, and all that there equals negative 2y. Okay, and now I'm going to divide both sides by 2x. 2x here as a factor with dx dy. It came out from the chain rule. So now see, I mistake again, but it's okay. Make the same mistake with me, and then you're going to learn. Okay, so dx dy equals, and I make the mistake again. Dx dy here equals minus 2y over 2x. It's completely forgivable that we can just keep mixing up, because, understandable that we set ourselves so far into using dy dx, so it became a habit. See what I'm saying now? But this here has a whole intention behind the scenes right there. Okay, and we can cancel out the 2. Our final dx dy here. Okay, that's not a mistake. It was just a little scribbling of my writing right there. So minus y over x. All right, so we have found our final implicit derivative from that equation. All right, and so let's try again. Let's try another one. So this time I am going to pick, so in part B, we are going to pick this equation right here, x squared y plus x y cubed equals 4. Okay, but I'm looking for dx dy. And so again, remind yourself, x is a function of y. X is a function in terms of y. So now, So x being intended as a function and y is a variable. But in the end, what we have here is an equation. So I am going to write from that equation x squared y plus x y cubed. I am going to take the derivative, but in respect to y as the variable. And equals on the other side, if it was a 4, a constant, but these twos are equal. So taking the derivative would be equal as well. So their two derivatives will be equal. Okay, and so now once again working on the easier side, the constants right here is easy regardless of what variable, whatever variable you're finding. Your function is a constant, and so taking the derivative must give you a 0. Okay, and so now the sum rule is breaking in right here, because we have a sum of these two terms, and each term involves all that crazy, the xy and xy all over, and we'll get to that. And so now I'm looking at, we need to find a separate derivative in terms of y for x squared y plus a separate derivative in terms of y for xy cubed. And I kind of misplaced my line right here, so I'll rewrite them equal 0. Okay. All right, and so now we are ready for the next step. So this first term, notice how it has a product between the x squared y, okay? And then this next term right here, notice how it has a product between the xy squared right there. So now in my next step, the plan here, I am going to work out with that part right there. It's a product rule, it's a product. So product rule must apply, right? So now ready into my next step. So the product rule says we have to find the derivative in terms of y of the first factor and multiply with y with our derivative plus. And now we're going to leave the first factor the same and multiply with the derivative in terms of for the function, for that function y in terms of the y variable. Okay, and so that one's easy. That term right there, that factor right there, because it's already explicitly defined. The main derivative, the derivative here is looking for x, is targeting y as the main variable. So here it's already in terms of y, it has already been explicitly defined as a function of y. It's a y to the first power, and so you just simply apply the power rule. So that here becomes just x squared times 1. Okay, and then here x is a function of y. X is a function of y, and so what I have here is x is a function of y. So the x squared there, okay, we can think of that as a squaring being the outside function, and inside of that there's a whole x which is already a function of y inside of that. And so taking that derivative, chain rule says we're going to take the derivative of the outside, so it becomes 2x, and multiply with the derivative of the inside. And remember, we are defining x implicitly as a function of y. So when we come to the derivative, it has to be again an implicit derivative. So it's a dx dy here. Okay, and so now these two terms immediately becomes so 2x for that, 2x times dx dy for that terms, and times y, and then plus x squared plus 1. That's how these two terms become. But now I'm not done really. All of that here takes care of my derivative of the first term. And now I'm going to underline the next term here. Okay, the next term here has a product again of the two factors, x and the y cubed like that. All right, so in my next step, add, and so the product rule say I'm going to take the derivative in respect to y of the function x, multiply with y cubed, okay, plus, now I'm going to leave the first one here the same. okay, and multiply with the derivative of y cubed in terms of y, and all that there equals a 0. Okay, so my writing is getting a little squeezy here, but this 0 is the right hand side, and all these two terms are here. Once again, x is an implicit function of y right there. So dx, dy, we didn't know what x is as a function of y. We only know that it's defined implicitly. And so we have no choice rather than just leaving that as an implicit derivative. So it's dx, dy here. That comes down for this, multiply with y cubed. And then all that there is now plus x times. So this is taking the derivative, but in respect to the y variable, and our expression has already been in terms of y. So this is explicit here. We're going to take the derivative. So it's just 3y squared. So x times 3y squared. And all that there equals 0. All right, so now let's clean up the terms right here. So in my next step, it's just a matter of rewriting the terms. First term becomes 2xy and see, I already had a mistake right here. I should have written in my earlier step. That should have been dx dy right there. And I wrote dx. Okay, so this is 2xy dx dy plus, and here it's just simply x squared. Okay, plus, and that term right there is a y cubed dx dy plus. Now I'm looking at 3xy squared equals 0. Okay, and so now after seeing quite a few examples prior to this one right here, then we can go ahead and combine like terms. These are the non-dx dy terms right here. Bring them to the opposite side. And then in the meanwhile, I'm going to speed up the process a little bit. I'm going to combine these two like terms. They are like terms in a sense that they have the common factor dx dy. So I'm going to be looking at xy plus y cubed, because these two terms right here, after factoring out the dx dy. Dx dy, okay, so 2xy plus y cubed times dx dy equals all these non-dx dy terms. I'm going to bring them to the opposite side. So now it's minus x squared minus 3xy squared. Okay, and so now we are ready to solve for this final dx dy over here. So it's just a matter of dividing that away, that expression 2xy plus y cubed right here. So dx dy equals to minus x squared minus 3xy squared, and we're dividing that by 2xy plus y cubed. Okay, and this is our final answer. Or maybe let me go back to the other board and to write down the final answer there on my other board right there. Okay. All right, so final answer for this problem is here. We found dx dy for this problem. Dx dy here is going to be minus x squared minus 3xy squared, okay, all over 2xy plus y cubed, and that's our final answer. Okay, and once again, of course, we have gone a long way, so forgive me if I made any typo errors that came out from typos. All right, but that's how we have been finding implicit differentiation. I mean, applying the technique of implicit differentiation. It's a technique so that we can take derivative implicitly right from an equation where any of our function can be implicitly defined in terms of as a function in terms of the other function. All right, and now I'm going to take a moment to erase my board, and I'm going to complete our lesson here with another example where we're going to find tangent line again. We did one in the beginning, but I'm going to create another one where we're all going to find it all from scratch right here. All right, and so now finding tangent line is the best place where we apply our skills in finding derivatives. So when it comes to this, I can leave the derivative steps for you to take, okay? And then I'll just help in with the other steps to remind you the general structure for finding any equation of any tangent line. So example 4, how's that? All right, so here in my example, find the equation, okay? Find the equation of the tangent line. To the equation. So x squared over 16 plus y squared over 9 equals 2. Okay, so find the equation of the tangent line. All right, the tangent line to this graph right here, and the graph came out from this equation at and the complete point. So here we have to give the complete point 4, 3. So this is our tangent point right here, and this tangent point exists on the graph, whatever the graph of that equation, and we want to find the equation of the tangent line. All right, and so take a moment to think of the plan right here as I'm erasing the board. And so now, to begin any tangent line problem, the first thing is to get the slope, because any line of y equals mx plus b, and our particular line here is a special line, it's a tangent line. So I always use that subscript, capital T right there. All right, and so now to find the subscript, capital T, your first step right here is to find the derivative, okay, the dy dx. And now we're getting back to just the usual dy dx. Even though, as a matter of fact, it shouldn't matter too much, okay? At this point, being able to find derivative implicitly, you should, I mean, the x dy or dy dx is pretty much all going to get it work. But so here's the thing. I mean, if you go with dx dy, it's going to be a little trickier, because you see, your final equation is written as a function in terms of x. And so that's why your derivative here has to be a dx, has to be a dy dx. If you were the same, but see, equation is an equation. The same tangent line can also be written as some x equals a different slope, mt y plus b right here. If you are attempting to write your equation in the form of x as a function of y, then you can start out by finding the dx dy, okay? And that's my intention for this kind of problem right here. Because like I said, if any of you follow really closely with my lecture up to this point, why does it have to be dy dx, where we can also find it as a dx dy? But, yes, you are correct, but you have to know that you find this for when your equation is being in this form. If you decide to go with this form, x equals mty plus b, then you're going to start out by finding the dx dy, and that's the whole point. So, but let's stay with things that everyone has been comfortable with. This one here, including me, I'm more comfortable with this form, okay? And so now dy dx, now I can leave that for you to use your skill that you have learned so far in finding implicit differentiation, right? Get me the derivative for that function right there, for that equation, okay? All right, so hopefully at this point you've had some thoughts about that. And so I can throw in one step before that, but your successful taking implicit differentiation at this point is going to be, it's a 2x over 16 plus, and then 2y over 9, but times a dy dx, right? And equals a 0, okay? And this is a 9, by the way, okay? And so in that way, our final dy dx here must be going to be, it's going to be a minus 2x over 16 divided by a 2y over 9 right there. And in other words, okay, and so our final dy dx here is a minus 9x over 16y algebraically. Okay, minus 9x over 16y. And so in that way, now the slope of the tangent line is going to be whatever we have found for our general implicit differentiation, but evaluated at the point, the given point 4, 3. This is our given tangent line. Okay, and so once again, let me quickly bring up the picture so that you can see the reason why tangent point must be given as a complete point right there. So for our graph right here, x squared over 16 plus y squared over 9 equals 2. It's an ellipse. Okay, so the graph for that is an ellipse. And so being an ellipse right here, so now with the value being 4, 3, or maybe let me quickly generate that point right there. 4, 3, it's that point right there. Okay, and then so with this point right here, then it's going to be, we're going to have, see, if we simply just give x equals 4, then we are going to end up with 2 different y values, and consequently we will have 2 different tangent lines. And so to specifically indicate what tangent line we're looking at, we have to give the complete tangent point with x and y coordinates, x and y values are being given. All right, so that's a quick, some quick developments about the problem. But now let's get ready for the problem right here. So back to my slope that I'm halfway found, that I'm halfway on my way finding it. Then the dy dx here substituted in the pair of values 4, 3. So that means we have 9 times minus 9 times x value is 4 divided by 16 times y, but y here is 3. Okay, and so our final value for this is going to be, now some algebraic cancellations for the algebra can come out. And so we're looking at minus 3 over 4, which is, you can think of that, I recommend keeping a fraction like that, or you can think of that as a negative 0.75. So that's your slope, and I don't even think I need to put this in a box right there, because it's not even our final answer. All right, so we got the slope of the tangent line. So the line has to look like this. Y equals, the equation of a tangent line must be y equals minus 3/4 x plus b. Okay, and so it's a halfway done equation. So now when it comes to the tangent point, we already had a tangent point given. I just want to briefly remind that for anyone, as a general step, as a general picture of finding the equation of a tangent line, we always need to indicate what tangent point we're looking at. That's the point being 4, 3. Okay, and so now for our equation, we are looking at, I can just use my, and you got your own control over this to have your own way of finding the y-intercept. So I'll go with 3 equals negative 3/4 times 4 for x plus b. And then from there we can solve for our value b to equals, so the 4 cancel with that, so b equals 6. So our final tangent line here, equation of a tangent line is y equals negative 3/4 x plus 6. All right, so that's our equation of a tangent line. So now I can go ahead and show you that on the picture here. Okay, that's still not the correct line yet, so let me hide it away. All right, so the picture is here. So now let me bring up the actual graph. All right, so now you see this is our tangent point being right at 4, 3, and this line right here is that line being the equation for that is I typed it in decimal and I typed in -3 over 4x plus 6 right here, and I got this line in green, and that does look like being tangent to this ellipse at the point of 4, 3.